Partially completed box plot in Figure 1 shows the distribution of daily mean air temperatures using the data from the large data set for Beijing in 2015. And an outlier is defined as either a value more than 1.5 times the interquartile range below the lower quartile or um, above the upper quartile. And we've got three of the lowest air temperatures and the highest, and we're asked to complete the box plot and show any outliers. So we've got to get into the outliers straight away here. Right, let's work out the interquartile range. Now the upper quartile, we need to read this off carefully. So it's gone up 6 little squares, it's going to be 26.6. And I want to minus the lower quartile, which is 19.4. And this gives me an interquartile range of 7.2. So if I want my lower boundary, then it's going to be the 19.4 minus 1.5 times 7.2, and that ends up being 8.6. This means that 7.6 and 8.1 are outliers, whereas 9.1 is okay. And then we'll do the same for the upper boundary, which is going to be 26.6 plus 1.5 times 7.2, and this ends up being 37.4. So 32.5 is within that. It's not gonna be an outlier. Right, and now we can complete our diagram. So I need to put little crosses where 7.6 is and 8.1. Then ignoring those, I go for like my minimum value is going to be 9.1. And my highest value, 32.5. So there we go. This is our completed box plot. Using your knowledge of the large data set, suggest from which month the two outliers are likely to have come. So for Beijing 2015 large data set, the data was from May to October inclusive. And then because we've got some colder temperatures here, I know we've got some higher ones, but yeah, there were some colder ones. It's likely to have been later on in the year. And what we're looking for here is October. So coldest temperatures be in October. Using the data from the large data set, Simon produced the following summary statistics for the daily mean air temperature for Beijing in 2015. So now this is all the months from May to October. And we've got, so 184 values. The sum of the temperatures is as shown. And this SXX is defined in the formula book. You've not seen a lot of it. And it's your sum of x squared. So the temperature is squared and then summed minus the temperatures added and then squared divided by n. And to get the standard deviation, it's actually, you just need to divide by n and square root, which will take you back to here, which is what the standard deviation is. So we're going to get 4952.906 divided by 184 square rooted. This is 5.1882 or 5.19. Great. Now, Simon decides to model the air temperatures with the random variable t that follows a normal distribution with this standard deviation and the mean 22.6, which we could have calculated. We're asked to use Simon's model to calculate the 10th to 90th interpercentile range. Let's get a little sketch down. It's centered at 22.6. Now remember, the interquartile range is your middle 50%. It's from 25% to 75%. So we want to find out this range here, where I've got 10% there and I've got 10% there. Remember, the 10th percentile is the position where like 10% of the data is below it. And the 90th percentile is where 90% of the data is below it. So you can see I put 10% at the upper end because that area there would be 90. So I'm gonna, what shall I call it? I'm gonna say that this is like x1 and this is x2. And we want to find out x2 minus x1. And I can write down that the best approach, I think, is we either go with, all right, no, let's do this one. So the probability that um, t is less than x1 is going to be 0.1. You could alternatively do the probability that t is less than x2 is 0.9. Absolutely fine either way. And now we can do inverse normal. Actually, another question in this paper, we have to do inverse normal, so I find it a little bit surprising. But anyway, so 0.1, we're going with, what was it, 5.19 and 22.6. Now this gives 15.9487. I got two options. You can do a very similar calculation for x2, or you can just find, you don't even need to, you can just find the difference between, because this is a symmetric distribution, we can find the difference between 22.6 and that 15.948, and then just double it. That's going to be the quickest approach, to be fair. And this gives 13.303, or 13.3. Finally, another large data set aspect, state two variables from the set that are not suitable to be modeled by a normal distribution, giving a reason for your answer. So you need to know this really well. So daily mean air temperature was okay. Rainfall. Rainfall is not okay because there's lots of zeros. It's just not going to fit this kind of curve very well. So basically, yeah, rainfall, lots of days with zero rainfall, it's not going to be symmetric. That's one of them. Daily pressure, no major problem in trying to model with that. The other one is going to be daily mean wind speed, Beaufort conversion, because this is qualitative data. So make sure you write down, these two and give your reasoning.